On the surface of an average planet circling an ordinary yellow star, an advanced intelligence searches the skies for evidence of life. Directed by even higher intelligence, machines with brains of silicon patiently sift through faint shards of radio data for the unmistakable signal that will indicate the first sign of life beyond Earth. In 1959, physicist Philip Morrison was co-author of the first scientific paper to suggest a strategy for such a search.
What I would like to know is an answer to a very simple question. Are we alone as conscious beings in this entire buzzing 400 billion star galaxy, one of 10 to the 10th other galaxies? It seems pretty implausible.
It's an enormous task to search the skies for intelligent life, looking for a golden needle in a huge cosmic haystack. But SETI, the search for extraterrestrial intelligence, has come a long way since early experiments by young radio astronomer Frank Drake. In 1960, Drake made the first radio search. He called it Ozma, after a princess from the fictional land of Oz. Now plans for the most sophisticated SETI search ever focus on the Goldstone Deep Space Communication Complex in California's Mojave Desert. It is the site of tests for a possible future NASA project. For Carl Sagan, a proponent of SETI for many years, this technical progress has made the present unique.
For the first time, we're mustering substantial, sophisticated, serious scientific searches for extraterrestrial intelligence. There's never been a time like that before. So there is some chance that in the next few decades we will get a signal of spectacularly distant, spectacularly exotic civilization, and everything on Earth will in that time change. That is possible.
NASA's proposed search focuses on radio, a portion of the electromagnetic spectrum where nature produces the least interference for any intelligent signal. The plan is to use existing radio antennas and combine them with advanced computer hardware and software specifically designed for the task. Signal processing equipment suitable for SETI is constantly becoming more powerful and more efficient. Contemporary SETI is a science, a discipline which transforms humanity's age-old speculations about life in the universe into experimental reality. SETI pioneer Frank Drake came up with a way to organize our developing knowledge and current ignorance. SETI scientists often use what's called the Drake equation to illuminate the necessary conditions for contact and to provide a rough estimate of the number of other civilizations. The existence of other technical civilizations depends upon astronomy, how planets form, comparative planetology, biochemistry, the role of intelligence in evolution, technology, and the fate of technical civilization. So SETI becomes a way to test our theories of the origin and evolution of the universe and the place of life within it. Some factors in the Drake equation are well determined, others are not. We're pretty sure our galaxy has about 400 billion stars, and maybe 10% of them will shine long enough for life to evolve. And we understand something of the life cycle of those stars. We know that it required colossal supernova explosions to transform the simple elements produced in the Big Bang into the heavy elements that form rocky planets and ourselves. And we have taken the first steps in understanding the chemical origin of life and the principles of evolution. But as yet, we've found no definitive proof of solar systems beyond our own, though recent observations of the disk of matter around the nearby star Beta Victoris suggest that planets may be common. In our own solar system, we have found no signs of advanced life, though planets like Mars and the large moons like Europa and Titan may have provided suitable environments for life in the past, or may do in the future, and seem worth further exploratory missions. So far, we have detected no signals from other civilizations around other stars, using technologies which could make them visible across the light years. And we cannot predict whether civilizations with advanced technology will perish quickly or learn to use it to explore the universe and thrive for the lifetime of their star. Some people look at the 7 conditions Drake proposed and see a weak chain that could easily be broken. Drake himself thinks there could be many thousands of civilizations with whom we could communicate in the Milky Way alone.
Look at, take the solar system, which we know has happened, the life on Earth, as typical. And as far as we know, it is typical. We know of nothing, no freakish event that was required for us, with our motorcycles and our videotape recorders, to exist.
SETI researchers such as Harvard's Paul Horowitz doubt that the question of other life in the universe will ever be answered in the abstract.
People have argued for a long time about the odds. What are the probabilities that there's life elsewhere in the universe? And lacking any data, they're nothing but argument. And you can argue yourself blue in the face, but if you want to answer this question, you're going to have to do the experiment.
But how can you do the experiment? What is the right experiment? Over interstellar distances, there's little sign of Earth. The sun outshines the planet by more than 1,000,000,000 to 1. That's one reason we've not yet seen planets around other stars with even the largest optical telescopes. It's rather like trying to see a firefly perched on the rim of a searchlight. But at radio wavelengths, at certain times and certain frequencies, Earth's technology outshines all other sources in the solar system by nearly 1,000,000 to 1. The carrier waves of Earth's radio and television broadcasts leak outward in a spherical shell and could be detected by distant civilizations. Radio signals travel at the speed of light, the fastest velocity possible. That's one reason NASA researchers think it is communication, not physical travel, that makes most sense for all species everywhere in the universe. Earth's most sensitive antennas could detect strong signals from halfway across the galaxy. The NASA effort has united Barney Oliver and other longtime SETI proponents with a younger generation of computer builders and programmers, including Kent Cullers, who, despite being blind, has worked on the statistics of pattern recognition.
Pioneer 10 is simply a very good example of the kind of signal that we might detect. First of all, although it's kind of close in interstellar terms, it's very weak. One would expect that a civilization would be farther away and stronger. It's near the limit of our detection. It's also a good example of a signal that might be used to speak.
The test was successful, even though the rotation of the Earth and its motion through the galaxy continuously changes the frequency of Pioneer's signal over time.
Promising candidate right here. We'll have to wait for a few more spectra to see if it, yes, I think that's it. This bright line you see going slanting down the screen is the signal from the Pioneer 10 spacecraft.
Now, if you look at other means of communication or main contact, you have to send something. You can't just think about it. You have to send something. And we've investigated all the known particles, and it's certainly true that electromagnetic waves or photons are hands down the best medium to use.
So it might seem that we have solved the problem of how to do the SETI experiment. Look for artificial signals at radio frequencies. Unfortunately, it's not that simple. Consider a terrestrial FM radio dial. On Earth, we recognize the channels of our favorite radio station, defined in megahertz, and can tune from one to the other. Each station has an assigned place on the dial. There, it broadcasts the carrier wave that's always present, no matter the program content. The stations are separated from each other so that they do not interfere. On the cosmic radio dial, we're also looking for signals artificially concentrated in frequency, but we don't know what frequencies the extraterrestrials may be using. On Earth, between 90 and 92 megahertz, there are just 10 frequencies in use. On the cosmic dial, there are 20 million potentially usable frequencies. In space, the entire electromagnetic spectrum could be used for communication, but in practice, some portions of the cosmic radio dial are harder to use.
There is a preferred region in the electromagnetic spectrum, we believe. It minimizes the energy required to make contact. That is in the microwave region. And the reason for that is that the noise that would interfere with our transmissions or theirs is lowest there. You go lower in frequency, the noise increases. Those noises that the galaxy produces. You go higher in frequency, quantum effects come in and create noise. And in this silent valley between those two walls, communication can be accomplished with the least energy of any region of the spectrum.
But even if there are clues about frequency, you still must choose where, when, and exactly how to listen. It's really more like looking for a needle inside a haystack. Inside a haystack. For simplicity, SETI researchers compare their experiments using 3 parameters. In addition to frequency, you have to choose directions, to survey the whole sky, or to target individual stars. And all experiments will have different sensitivities, determined primarily by the size of the radio antenna and by how long they listen. Are there any further clues which can help limit places to look for the needle? Many SETI researchers think there may be, at least in the frequency dimension. Since hydrogen is the most abundant element in the universe, they argue that all intelligent species would think of transmitting their signals close to the frequency at which hydrogen atoms naturally emit radio waves. 1420 megahertz was the first so-called magic frequency to be tried. It was at 1420 megahertz that Frank Drake searched in 1960, the first targeted search. He looked at just 2 stars at this one frequency in a search of moderate sensitivity. In 1973, Ohio State University, with its unusual antenna, began a continuing sky survey. It listens not to single stars, but to the sky passing overhead. It covers 50 channels, but is low in sensitivity. Searches over the last 6 years by myself and French radio astronomer François Bureau at N.A.S.A. have looked at 350 stars in the latest targeted search. There has been significant international interest in SETI, with searches mounted in the USSR, Canada, Holland, Germany, and Australia, as well as those in the United States and France. At N.A.S.A, by adapting existing radio astronomical equipment, we've been able to listen to thousands of channels channels simultaneously. We've achieved improved frequency coverage and a modest gain in sensitivity. As computers advanced, it became possible to construct detectors that were specially adapted to the needs of SETI. One of the first researchers to take advantage of this capability was Paul Horowitz, a professor of physics at Harvard University. The key breakthrough was the ability to scan many channels and frequencies simultaneously. The heart of the system is a so-called multi-channel spectrum analyzer, or MCSA. The one Horowitz uses in his latest system was designed in collaboration with Ivan Linscott and colleagues at Stanford University as part of the R&D for NASA's planned SETI system. Horowitz puts this equipment to practical test in a sky survey known as N.A.S.A, the Mega-Channel Extraterrestrial Assay. Drake's experiment could scan only one frequency channel at a time. N.A.S.A can listen to 8.4 million frequency channels simultaneously. It can do in 1 second what took Drake 5 years. N.A.S.A, funded by the Planetary Society, is perhaps the ultimate magic frequency machine. But if Horowitz has guessed wrong, he may be looking in the right direction with excellent sensitivity, but just the wrong frequency. No search to date has found any evidence of intelligent life, but SETI researchers feel that their equipment has not been equal to the task. NASA's goal is to extend these previous efforts into a truly comprehensive search. Successful tests of hardware and software in detecting signals like those coming back from Pioneer are but the first step in a planned 10-year project that will combine the most promising strategies from these earlier searches.
The NASA approach that we're developing right now has two different approaches to the search, and they're complementary. One of them is called the Sky Survey, and another is called the Target Search. And the objective of the Sky Survey is to search the entire sky, making no guesses to what are the best directions. To carry out that search in a reasonable length of time, we have to do it quickly, which means we sacrifice sensitivity to the signals. We only detect maybe the strongest of the signals that might be there.
To cover the sky quickly, the radio telescopes will be driven very rapidly, eventually scanning each patch of the sky 30 times. But it is in frequencies sampled, rather than directions covered, that NASA's project will dwarf all previous searches. Drake's lone frequency is gossamer thin in comparison to the tens of billions of usable frequencies in the naturally quiet microwave window. And even though the Ohio State survey covers lots of directions and stars, about 60% of the sky overall, its frequency range is also limited. N.A.S.A also scans the northern skies, but all of its 8.4 million channels cluster around a single magic frequency, though it will be tuned to others. In contrast, on the frequency dimension, NASA's sky survey will cover the whole 1 to 10 gigahertz window and the entire sky. To achieve this comprehensive coverage of directions and stars, NASA plans to use several telescopes around the world, which are part of its spacecraft tracking system. Each of these telescopes can see 2/3 of the sky, and NASA will move its sky survey system between them.
The complementary approach is to say, let's concentrate on detecting with more sensitivity, be able to detect weaker signals. And to do that, we look at one in a few directions for longer periods of time, and that's called targeted search. And we pre-select a set of stars that we know a priori are more or less similar to our own sun in age and size, and look in those directions with more sensitivity and the ability to detect maybe more complex signals.
The targeted search will look repeatedly and at different frequencies at nearly 800 nearby stars. Like N.A.S.A, NASA's targeted search may start around 1420 megahertz, that is 1.42 gigahertz. Then it will expand to cover all frequencies between 1 and 3 gigahertz. Like the Sky Survey, the targeted search requires antennas around the world. The giant radio telescope at Arecibo is the largest on the planet, and because of its unique size and sensitivity, NASA hopes to share time to search for the very faintest signal. The large dish can't be moved, so it can only see stars which rotate overhead each day. The antennas at either Ohio State or N.A.S.A could be used to observe about 300 stars outside the range of Arecibo. More of the target stars can be seen from the southern hemisphere, so about 200 of them could be observed from the large NASA antenna at Canberra, or perhaps the astronomical facility at Parkes in Australia. The last 50 or so stars must be searched from a telescope in the northern latitude, perhaps rather appropriately from Greenback, where Frank Drake began the search with Project Osmo. With this unparalleled combination of advanced hardware and sophisticated software, NASA's project will have the capability to revolutionize SETI. The targeted search will look for faint signals from what, according to the current understanding of cosmic evolution, seem to be the most interesting sights, and will look at billions of frequencies. The Sky Survey will cover an even wider range of frequencies, yet with sufficient sensitivity to detect a very strong signal from clear across the galaxy. In addition, NASA's system will have an unprecedented ability to look for different types of signals that vary over time, not just a continuous carrier wave like that of Pioneer 10 or Earth's radio broadcasts. For the first time, we will be able to detect regular pulses that some researchers say will save energy and so be the choice of the transmitting civilization.
The interesting thing about the SETI search is that although we claim that we're looking for extraterrestrial intelligence, we can't actually define what an intelligent signal is. And so a starting point is to say we look for a signal which nature will not produce by any mechanism that we understand.
Kent Cullers helped NASA design the smart computer algorithms needed to locate weak signals in the many channels of noise. But there will be no human staring at sophisticated graphics displays. No human is any more sighted than Kent when it comes to recognizing an extraterrestrial signal.
The eye is not a good detector, first of all, in sensitivity. A thing that you could look at virtually forever and you would never know whether you were seeing random noise or whether you were seeing a real signal. The computer can find signals that are 10 times weaker than that. The amount of data processed per second is the equivalent of the entire Encyclopedia Britannica per second. Now, of course, that's filled with random letters, if that's analogous to noise. And what you have to do is find out one pattern that says hi there in all of those random letters that come in every second, and then decide whether that pattern could have happened at random because of your statistics of your process, or whether, in fact, that's the real thing. And a human being, even if he could perform the task as effectively as a computer, couldn't do it for very long.
Removing humans from the signal detection process requires very special hardware, which is what Ivan Linscott and his colleagues at Stanford University have been designing.
And that's like having 10 million ears, each one listening to a particular tone, and where all of those are listening simultaneously. And so what we're doing now is taking the technology that exists in this prototype form and casting it in sand, building silicon versions of our processors that together with the way we know how to use them will condense both the scale and increase the performance. It no longer will require you to step in small chunks across the frequency band. You can make giant strides and spend lots of time on particular sources or sweep broad swaths of the sky. And I think there's where the opportunity lies, because it's a prospector's art, and you just have to look and take your best bet.
In normal operations, the NASA systems will rely very heavily on silicon intelligence with limited human involvement. The computers will have to have sufficient online intelligence to analyze the vast amounts of data arriving every second and weed out the inevitable false alarms before involving humans. For the operational sky survey, the sky will automatically be divided into blocks, which will be searched in turn. NASA expects many suspicious signals during each scan, but they won't be from extraterrestrials. These events will be compared to the online database of radio frequency interference, RFI, to identify man-made signals. Most of the signals will be explained away until someday, maybe, there might come something more significant. The characteristics of the long-hoped-for signal will show some clear sign of intelligence, and the computer will have made contact. Then it will call humans to come look, and we will know for sure about life elsewhere in space.